Right now, as you're hearing this, Mars is somewhere between 55 and 401 million kilometers away, and there is no way to know which without checking the date. That's not a rounding problem. The distance to Mars changes by more than twice the width of Earth's entire orbit, over and over, forever. And the single number printed under Mars in every textbook you've ever opened has never once been the answer. So here's the question that sounds simple and isn't. How far away is every planet from Earth? Not how far each planet sits from the Sun. That's the number you were given, and we'll get to why it's the wrong number. I mean the gap between you, standing where you are, and each of the other 7 worlds. 8 if you still count Pluto. And we'll deal with that too. There is an answer. It takes about an hour to build it properly, and by the time we're finished, you'll know something most people never find out. Which planet is genuinely our nearest neighbor, and it isn't the one you're thinking of. Start with the ruler, because everything depends on it. 1 astronomical unit is the yardstick of the solar system, roughly the distance from Earth to the Sun. Since 2012, it hasn't been measured at all. It's been defined. Exactly 109,597,870.7 kilometers, fixed by international agreement, because the measurements had become more precise than the definition they were serving. Light crosses it in 8 minutes and 19 seconds. The sunlight landing on your window left the sun before you noticed it. Every distance from here forward is built on that unit, and there's no version of this story where it turns out to be smaller than we thought. Now the numbers under the pictures. Mercury, 58 million kilometers. Venus, 108 million. Mars, 228 million. Jupiter, 778 million. Saturn, 1.43 billion. Uranus, 2.87 billion. Neptune, 4.5 billion. Every one of those figures is accurate. Nobody's hiding anything. Nobody's made an error. They're just answers to a different question. Each of those is a semi-major axis. It describes the average size of that planet's own loop around the sun. It's a fact about the relationship between one planet and one star, and Earth doesn't appear in it anywhere. When a diagram writes 228 million kilometers under Mars, it's telling you how big Mars's racetrack is. It has never told you how far Mars is from you, and it was never trying to. But that's exactly how everyone reads it, because it arrives already shaped like an answer, and there's only one number on the page. Here's the plainest version. Mars has never been 228 million kilometers from Earth. Not on the day you were born, not on any single day of your life. It's been 55 million away. It's been 401 million away. It's spent time at almost every value in between. The specific figure under its picture describes something that simply isn't the gap between us, and couldn't be, because that gap isn't the kind of thing one number can hold. Both planets are moving. Earth goes around the Sun at 29.78 kilometers per second and finishes a lap in 365 days. Mars travels at 24.07 and takes 687. 2 objects on 2 different circles at 2 different speeds. The distance between them isn't a property of either one. It's a property of the moment, which means the honest answer for every planet on this list isn't a figure. It's a range, and the ranges behave in ways nobody warns you about. Let's walk them, starting from the inside. Mercury first, and Mercury is where the whole intuition begins to come apart. Mercury orbits the Sun at an average of about 58 million kilometers, but it doesn't sit there. Its orbit is the most stretched of the 8, with an eccentricity around 0.206, which means over the course of its 88-day year, Mercury swings from roughly 46 million kilometers out to about 70 million. It is 50% further from the Sun at one end of its year than the other. The number under its picture isn't a place Mercury lives. It's the midpoint of a continuous slide, occupied for an instant, twice per orbit. From Earth, Mercury's distance runs between roughly 77 million kilometers at its very best, and about 222 million at its worst. Light takes a little over 4 minutes to reach it on a good day, and around 12 on a bad one. Now hold that against Venus, because Venus is supposed to be the winner here. Venus at its nearest comes within about 38 million kilometers of Earth. That's the smallest gap between our planet and anything in the solar system except the Moon. Nothing else ever gets that close. Light crosses it in just over 2 minutes. So Venus is our closest neighbor. That's what you were taught, that's what the encyclopedias say, and it has been the standard answer for well over a century. It's wrong, and the way it's wrong is one of the strangest small failures in the history of science. Look at what the traditional calculation actually does. Earth's orbital radius is 1 astronomical unit. Venus's is 0.723. Subtract, and you get 0.277 AU, about 41 million kilometers. Do the same for Mars, and you get 0.524, about 78 million. Venus is smaller, so Venus wins. But that arithmetic didn't compute a distance between two planets. It computed the gap between two racetracks at the single point where they come nearest. That's a configuration that exists for a moment and then doesn't recur for over a year and a half. The rest of the time, Venus is somewhere else entirely, and a good portion of the time it's on the far side of the Sun, 261 million kilometers away, further than Mars is at Mars's closest. The geometry of two circles is such that most possible arrangements are not the close ones. The old sum quietly assumed a planet spends its life at its best moment. In March 2019, 3 engineers named Tom Stockman, Gabriel Monroe, and Samuel Cordner published a short piece in Physics Today under a title that reads like a correction slip. Venus is not Earth's closest neighbor. They used no new observations and no new instrument. Every quantity in their argument had been available since Kepler. What they did was replace the moment with all moments, treat each orbit as a circle, share a plane, and compute the average distance from a point on one to every position on the other, weighted properly for the time spent at each. The result comes out as an expression involving a piece of 18th century mathematics called a complete elliptic integral, which exists precisely for problems about the shapes of ellipses. Then, and this is the part I like, they checked it by brute force. They ran millions of position samples using astronomy software and simply measured the distances and averaged them. No cleverness, just counting. The elegant method matched the simulation to within about 1%. The old subtract the radii method was off by as much as 300. Here are the real figures. The average distance from Earth to Mercury is about 1.04 astronomical units. To Venus, about 1.14. To Mars, about 1.69. Mercury is our nearest planetary neighbor. Not on its best day, Venus takes that easily. But averaged across any span of time long enough to be called typical, Mercury is closer to Earth than Venus is, by something on the order of 15 million kilometers. Their simulation makes it concrete. Ask on any given day which planet is currently nearest to Earth, and across thousands of years the answer came back Mercury, roughly 47% of the time, Venus about 36, Mars about 17. Mercury isn't just closer on average, it's the most frequent answer to the question, on roughly 1 day in 2. The reason, once said out loud, is almost embarrassing. Mercury is trapped in a tight loop near the Sun. It can never get more than about 70 million kilometers from the star. We're also fairly near the Sun. So the absolute worst Mercury can do is Earth's distance plus its own, and that ceiling is low. Venus, on a wider orbit, swings much further out on its bad days. Venus wins the sprint and loses the marathon. And it generalizes in a way that's genuinely hard to shake off. The same paper notes that Mercury is the closest planet on average to each of the other 7. Not just to us, to Venus, to Mars, to Jupiter, Saturn, Uranus, and Neptune. There is one world in this solar system that is on average nearer to everything than anything else is, and it's the smallest, hottest, most ignored of the 8, pressed up against the star. Redraw the map by nearness rather than by radius, and Mercury sits at the hub, connected to every world at once, with the sun off to one side as a detail. That map has never appeared on a classroom wall. I should be fair about the method's limits, because being careful is part of why the result holds. It works as well as it does because our 8 planets happen to travel on nearly circular orbits in nearly the same plane. Feed it something wildly eccentric or steeply tilted, and the approximation starts to fray, which is exactly why the authors didn't stop at the formula and went to the trouble of simulating thousands of years of actual positions. And I want to be fair to the old sum too, because there's something buried in it that matters enormously later. Subtracting orbital radii is not meaningless. It's the answer to a completely different question, and as it turns out, a more useful one for anyone who actually wants to go somewhere. Keep that filed away. In about 20 minutes, it's going to rearrange the entire solar system. So we've lost the number and we've lost the ranking. Let's keep walking outward and watch what happens to Mars, because Mars is where the swing gets violent. Mars is the planet everyone quotes and nobody quotes correctly. At its theoretical closest, Mars can come within about 54.6 million kilometers of Earth. At its furthest, sitting on the opposite side of the Sun, the separation stretches to roughly 401 million. That's a factor of more than 7 between the best day and the worst. Between those two extremes, 346 million kilometers appear and disappear, which is more than twice the distance from here to the Sun, cycling endlessly. Put it in something you can feel. A radio signal to Mars at closest approach takes about 3 minutes. At its furthest, a little over 22. Same planet, same solar system. The only thing that changed is what day it is. The record approach has a timestamp, which is rare in this subject and worth having. On 27 August 2003, Mars came within about 55.76 million kilometers of Earth, the closest it had been in roughly 60,000 years. The last time it was that near, there was no writing, no agriculture, no cities. The next time it beats that mark is expected around 2287 point. Why so rare? Because a record needs 2 coincidences at once. Mars has to be at opposition, with Earth directly between it and the Sun, and that happens reliably about every 26 months. But Mars's own orbit is noticeably stretched, with an eccentricity near 0.093, so its distance from the Sun swings between roughly 207 and 249 million kilometers over its year. For a record, opposition has to land at the same time Mars is near the inner end of its own loop. Those 2 cycles drift against each other over long spans, so the good years cluster, then stop, then come back after a very long time, which is why oppositions are not equal. One year Mars comes within 56 million kilometers. Another year the best it manages is around 100 million. Both are described as Mars at its closest. One is nearly twice the other. There's a hoax that rides on exactly this confusion, and it circulates every August like clockwork. The message claims Mars will appear as large as the full moon in the night sky. At that record 2003 approach, Mars spanned about 25 arcseconds. The moon spans roughly 1,800. For Mars to look like the moon, it would have to be nearer than the moon. The hoax survives because it exploits the same instinct this whole subject keeps punishing. The assumption that close and close enough to see are the same idea. Now, before we go further out, I want to deal with the word average, because it's doing more than one job, and the difference is enormous. There are 3 quantities in circulation for Mars, and all 3 get called the average distance. The first is 228 million kilometers, the semi-major axis. That's a fact about Mars and the Sun, and should never appear in a sentence about how far Mars is from us. The second is about 227.8 million, the midpoint between 54.6 and 401. It lands almost exactly on the first figure, which is a coincidence of geometry that has done more to entrench the confusion than anything else. And it isn't really an average. It's the center of a range, the point halfway between the best case and the worst, which is a different concept from the typical case. The third is the one almost nobody quotes, and it's the only one that answers the question people are actually asking. Measure the gap every single day for a few thousand years, and take the mean, and you get about 1.69 astronomical units, roughly 253 million kilometers. The difference between the second and third is around 25 million kilometers. That's about 65 times the distance from Earth to the Moon, silently added or removed, depending on which meaning of one ordinary English word happened to be in the sentence. The true average is larger because Mars spends more of its life far from us than near. When two planets sit on opposite sides of the Sun, they linger there, and most relative positions simply aren't close ones. That's the pattern for the inner planets. Now watch it change as we go outward, because the further you go, the more honest the single number becomes, and that turns out to be the opposite of comforting. Jupiter sits an average of 778 million kilometers from the Sun, and from Earth, the separation runs between roughly 588 million and 968 million kilometers, a factor of less than 2, where Mars was a factor of 7. Light takes about 33 minutes to reach Jupiter at its nearest, and closer to 54 at its furthest. Saturn's orbit is about 1.43 billion kilometers out, and from here the gap swings between roughly 1.2 and 1.67 billion. Signal time, somewhere between about an hour and 7 minutes and an hour and 33. Uranus averages about 2.87 billion kilometers from the Sun. From Earth, roughly 2.6 to 3.15 billion, and the light takes between about 2 hours 20 and nearly 3 hours. Neptune, at about 4.5 billion kilometers from the Sun, varies from us only between roughly 4.3 and 4.7 billion. Just under 4 hours of light at best, a bit over 4 hours 20 at worst. Notice what's happened. Earth's entire orbit, the full 300 million kilometer width of our year, has shrunk to a small correction on a baseline of 30 astronomical units. Our own motion has stopped mattering. So Neptune genuinely does have something close to a fixed distance from us. Mars does not. And the cruel arrangement is that the planets near enough to be worth visiting are precisely the ones whose distances refuse to hold still. There's something else the numbers can't show you, and it's the thing that makes this list misleading in a completely separate direction. The picture in your head has these 8 worlds spaced like houses along a street. That arrangement doesn't resemble the solar system in any respect. Not approximately. Not as a simplification. It's a different shape. Every diagram you've ever seen has been compressed radially and unevenly, because if you draw it honestly, 7 of the 8 planets fall off the page. There's no printable rectangle that holds both Mercury and Neptune with anything visible in between. So the diagram cheats, because the alternative is a picture with 1 dot on it. Let me build the honest one instead. Take a beach ball about 60 centimeters across and set it on the ground. That's the Sun, at roughly 1 part in 2.3 billion. Now start walking. 25 meters out, put down a poppy seed. Mercury, at 42 meters, a peppercorn for Venus. At 65 meters, far enough that the beach ball behind you has stopped looking like something you could touch, place a blue bead 5.5 millimeters wide. That's Earth. Everything that has ever happened to anyone on a bead the size of a grain of rice. The Moon on this scale sits about 17 centimeters from that bead, and the entire orbit of the Moon, the full extent of everywhere human beings have physically traveled in the history of the species, would fit comfortably inside a dinner plate. Keep going. At 98 meters, a slightly smaller grain for Mars, and then nothing happens for a very long time. You walk past 150 meters, past 200, crossing the asteroid belt with nothing to put down, because on this scale the entire belt is dust you couldn't see if it were there. At 336 meters you finally stop and set down a plum. That's Jupiter, and you're now 1/3 of a kilometer from a beach ball you can barely make out. Saturn's at 618 meters, Uranus at 1,239. Neptune, the last of them, is 1,938 meters from where you started, nearly 2 kilometers. A 25-minute walk with the entire inner solar system contained in the first 100 meters of it and almost nothing in the remaining 1900. And if you wanted the nearest star on the same model, you'd need to keep walking for something like 17,000 kilometers. There's a second dishonesty stacked on the first. On the page, planets are drawn large enough to see, which means the ratio between world size and world spacing is off by a factor of around 1,000. In the model you just walked, Jupiter is a plum, and its nearest neighbor is 280 meters away. On the page, Jupiter's 2 centimeters across, and Saturn's 4 centimeters over. The diagram doesn't only squeeze the distances, it inflates the worlds until the emptiness vanishes, and emptiness is the actual subject. People have built this at full scale. The Sweden solar system runs at 1 part in 20 million, using the Ericsson globe in Stockholm as the sun, an arena 110 meters across, which on that scale is exactly right. Earth sits 7.6 kilometers away. Neptune isn't in Stockholm at all. Neptune is more than 200 kilometers up the coast. That's what an honest drawing costs. Not a bigger sheet of paper, a country. Now, every number I've used to build that walk was a tidy average, which means even that model is the best case, the version where each planet stands politely at its mean distance and waits. They don't wait, and once you accept that they don't, the distances stop being the problem, because there's a second layer underneath and it's worse. The path is not the gap. No spacecraft in the history of the human species has ever traveled to another planet. Not one. What they've done instead sounds like a quibble and turns out to be the most important fact in this entire subject. They've changed orbits. Here's your actual situation when you leave Earth. You aren't standing on a platform with a planet hanging in front of you. You're already moving at 29.78 kilometers per second in an enormous circle around the sun. So is your destination, on a different circle at a different speed, and neither of you can stop. There's no direction to point in that gets you there, because the instant you leave, you're still orbiting the sun. You've only changed which orbit. The man who worked out what to do about that wasn't an astronomer. Walter Hohmann was a German architect and municipal building surveyor who published a book in 1925 on the attainability of celestial bodies, worked out in the evenings. What he found was this: to move from one circular orbit to a larger one as cheaply as possible, you fire your engine once, briefly, in the direction you're already going. That doesn't aim you at anything. It just stretches your circle into an ellipse whose far end touches the orbit you want. Then you shut down and coast for months or years, and when you arrive at the far end, you fire once more to settle in. That's a Hohmann transfer, and a century later it's still essentially how everything gets anywhere. Notice what's missing. No pointing at the target, no steering, no holding a course. The whole journey reduces to one problem in timing. You have to arrange for the far end of your ellipse to touch the destination's orbit at precisely the moment that planet happens to be passing. Imagine sitting inside it. The engine's been burning a few minutes, and then it stops, and the silence is permanent. That was the whole burn, and there won't be another that matters for 259 days. You look out and Mars isn't in front of you. It's off to one side, well off. A small orange point nowhere near the direction you're traveling. You're not moving toward it and you won't for months. Nobody's flying this thing. Nobody will touch the controls. Every consequential decision was made before the engine shut down, and everything after it is patience. Now the arithmetic. A Mars transfer runs from 1 astronomical unit at the near end to 1.524 at the far end, and you ride half of it. Work out the length of that arc and you're looking at something on the order of 600 million kilometers of actual travel. Set that against the gap. Mars at its closest is 54.6 million kilometers away. The journey is roughly 10 times longer than the distance. And the minimum energy transfer times, once you accept the shape, are brutal in a very orderly way. To Venus, about 146 days. To Mars, about 259. To Jupiter, roughly 2 years and 9 months. To Saturn, around 6 years. To Uranus, about 16. To Neptune, somewhere near 30. 30 years. A person could begin such a mission at 25 and be 55 when it arrived, having done nothing in between but wait. Real missions don't fly pure home and transfers, because 30 years is unacceptable and because there's a trick available. But the trick makes the path longer, not shorter. Cassini went to Saturn, an orbit 1.43 billion kilometers from the Sun. The distance it actually traveled was about 3.5 billion, nearly 2.5 times its target's own distance from the star. And the route is almost comic. To reach Saturn, it first flew inward and passed Venus in April 1998, came back and passed Venus again in June 1999, swung past Earth that August, went out to Jupiter in December 2000, and only then had enough speed to coast the rest of the way. A spacecraft bound for the outer solar system spent its first 2 years going the wrong direction. Juno covered around 2.8 billion kilometers to reach Jupiter, a path several times longer than Jupiter's own distance from the Sun. And Messenger went to Mercury. The planet we established is, on average, our nearest neighbor in the entire solar system. It made 6 planetary flybys, looped around the Sun repeatedly, and covered something on the order of 8 billion kilometers over 6.5 years. 8 billion, to reach the house next door, the equivalent of 100 round trips to the end of the street. That's not incompetence, and it isn't caution. Those spacecraft took long routes for the same reason a heavy lorry takes a run at a hill. They were buying speed they couldn't afford to carry. There's a second reason the paths are long, and it's written into the laws of motion rather than into anyone's budget. Kepler's third law says the further out you go, the slower everything moves. Mercury travels at 47.36 kilometers per second, Venus 35.02, Earth 29.78, Mars 24.07, Jupiter 1306, Saturn 968, Uranus 6.80, Neptune 5.43. Read that list twice, because distance charges you twice for the same trip. The path to a far planet is longer, which is obvious, and the far planet is also moving more slowly, so the orbit you have to enter to match it is a slow orbit. The whole outer solar system runs on a lazier clock. Neptune drifts along at 5.5 kilometers per second. That's slower than some of the machines we throw at it, and it still takes decades to catch, because the distance is doing all the work and the speed is doing none. And you can't begin the fall whenever you feel like it. The door isn't always open. For Mars, the 2 planets return to the right relative arrangement every 779.9 days, about 26 months. That single number governs everything humans have ever done at Mars and everything we ever will. Every rover, every orbiter, every crude architecture anyone has drawn on a whiteboard. The practical window, the span of days on which a viable trajectory exists with the propellant you actually have, is typically 2 to 4 weeks. So the situation is a fortnight of opportunity recurring every 2 years and 2 months, and if the rocket has a fault or a software review turns up something unresolved, the cost isn't a delay of days. You can see that cycle written across world events. In July 2020, 3 separate missions from 3 separate nations left for Mars inside 11 days of each other. The United Arab Emirates launched the Hope orbiter on the 19th. China launched Tianwen-1 on the 23rd. The United States launched Perseverance on the 30th. 3 space programs on 3 continents with entirely different budgets and politics, all departing in the same fortnight. Not through coordination. The door was open, and it wouldn't open again until late 2022. The outer planets invert this completely, and the reason is quietly delightful. A window recurs at what's called the synodic period, and because Jupiter, Saturn, and Neptune barely move while Earth completes a lap, we come back around to the same arrangement roughly once a year. Windows to Mars are rare. Windows to Neptune are almost always available. The constraint out there isn't when you can leave. It's how long you'll be gone. So the second layer says the path is 10 times the gap and comes with a timetable. That still doesn't explain why Mercury should be so hard. It's right there. It's the closest planet on roughly half of all days. Reaching it costs more than reaching Saturn. Ask a mission designer how far away Mars is, and they won't answer in kilometers. They'll answer in kilometers per second, not distance. Change in velocity, delta V, the total amount of velocity change a spacecraft has to be able to produce, and it determines whether a mission is possible at all. Delta V rules everything because of the rocket equation, which is unkind in a specific way. A rocket carries its own propellant, and that propellant has mass, and accelerating that mass needs more propellant. The relationship between the velocity you want and the fuel you need isn't linear, it's exponential. Small differences in required velocity become enormous differences in what's buildable. Starting from low Earth orbit, departing for Mars takes somewhere around 3.6 kilometers per second. Departing for Jupiter, around 6.3. Saturn, around 7.3. That scales the way intuition expects. But departing is the cheap half. If you want to stay, to enter orbit rather than fly past and keep going, you have to stop. Roughly half the velocity budget of an orbital mission is spent on stopping, and that's the single most underappreciated fact in interplanetary travel. Do the full accounting for Mars and you're at something like 5.7 kilometers per second, all in. Do it for Mercury, and you're at roughly 13. Mercury, the nearest planet to Earth on average, the nearest planet to every other planet in the solar system, costs more than twice as much velocity to orbit as Mars, a world nearly 4 times further out. And it's comparable to, or worse than, injecting toward the outer giants. Convert that into something physical. With a good chemical stage, hitting Mars's 5.7 means roughly 3/4 of what you launch is propellant. Demanding, but completely normal. Every rocket ever flown looks something like that. Hitting Mercury's 13 pushes you towards something like 95% propellant. You've gone from a spacecraft that carries a lot of fuel to a fuel tank carrying a rumor of a spacecraft. Which is why nobody flies to Mercury directly. Messenger and Bepi Colombo both chose to pay in time instead, 6.5 years with 6 flybys for the first, and 8 years with 9 flybys for the second. Time is the one currency that can be substituted for propellant. The reason for all of this is the shape of the sun's gravity. We picture the solar system as a flat map. It's a funnel. The sun sits at the bottom of an enormous depression, and every planet sits somewhere on the slope, which is why Mercury has to travel at 47 kilometers per second and Neptune only at 5. Going outward means climbing, which costs energy and hands you a gentle arrival because you're slowing down as you rise. Going inward means falling, which gives you speed for free and then presents the bill, because all of that free speed has to be destroyed before you can stop. There's one more asymmetry, and it's why Mars is cheap in a way that has nothing to do with distance. Mars has an atmosphere. Thin, only about 1% of ours at the surface, but enough to brake against, and every successful Mars mission has used it, turning velocity into heat in a shield, instead of buying that change with fuel. Mercury has no atmosphere at all. Neither does the Moon. On airless worlds, every last meter per second of arrival speed has to be canceled by an engine-burning propellant you launched from Earth years earlier. A thin layer of gas is worth more in the accounting that matters than 200 million kilometers of position, which means the map mission designers actually use looks nothing like the diagram. On the diagram, Mercury's nearest and Neptune's furthest. On the delta V map, Mercury and Neptune sit at comparable difficulty, and Mars, significantly further away by every distance measure we've discussed, is one of the most accessible destinations in the solar system, which is a large part of why our robots keep going there. And remember the sum everyone got wrong for a century and a half? Subtracting one orbital radius from another, that's not the distance between two planets. But the difference between two orbital radii is a decent first indication of how much orbital energy you have to change, because energy depends on the size of the orbit rather than where the planet is standing today. For 150 years, textbooks were printing an energy figure and labeling it a distance, and nobody noticed, because nobody was asking about energy. The wrong answer to one question was quietly the right answer to a better one. So now we can finally convert all of it into the only unit any human being has ever experienced a journey in. New Horizons left Earth on 19 January 2006 at 1626 kilometers per second, the highest launch speed ever achieved by a spacecraft, fast enough to cross the Atlantic in about 6 minutes. 13 months later, it stole speed from Jupiter, cutting roughly 3 years off the trip. It reached Pluto on 14 July 2015. 9 years, 5 months, and 25 days. Our fastest launch ever, on a direct trajectory, with a push from the largest planet in the solar system, and the answer was most of a decade. Cassini launched in October 1997 and entered Saturn orbit on 1 July 2004. 6 years and 8 months, a full third of its 20-year mission spent simply getting there. Juno launched in August 2011 and reached Jupiter on 4 July 2016, 4 years and 11 months. Messenger launched in August 2004 and entered Mercury orbit in March 2011, 6 years and 7 months to reach our nearest neighbor. And Voyager 2, which turns this from a list into something else, launched 20 August 1977, Jupiter in July 1979, Saturn in August 1981, Uranus on 24 January 1986, Neptune on 25 August 1989, 12 years and 5 days from launch to the last planet. There's the answer. 5 years to Jupiter, around 7 to Saturn, 6.5 to Mercury, 9.5 to Pluto, 12 to Neptune. The distance to every planet measured honestly is a span of years long enough to contain a career. Consider what that does to people. Voyager's project scientist Edward Stone took the role in 1972, before the spacecraft existed. He was in his mid-30s. He was still in that job half a century later, having handed it on only in 2022, and he died in 2024, with both spacecraft still transmitting. That's what the distance costs. Not propellant. A working life, start to finish, spent on a single crossing that outlived him. And there's a fourth layer, the one no engine will ever shorten. Light travels at 299,792 kilometers per second, and nothing carrying information goes faster, which means every distance on this list is also a delay. To the moon, 1.28 seconds. Small enough to be almost conversational, and if you listen to Apollo recordings, you can hear people correcting for it. That's the last place in the solar system where speech is possible. To Mars, 3 minutes at best, 22 at worst. To Jupiter, half an hour or more. To Saturn, over an hour. To Uranus, nearly 3. To Neptune, about 4 each way, which makes a round trip 8 hours. You could send a command to a spacecraft at Neptune, go to sleep, and the confirmation would still be in transit when you woke up. Watch what that does to a real operation. Curiosity reached Mars on 6 August 2012, with an arrival sequence involving a heat shield, a supersonic parachute, a rocket-powered descent stage, and a maneuver where that stage hovered and lowered a 1-ton rover to the surface on cables. The whole thing was designed to take about 7 minutes. The one-way light time that day was 13 minutes and 48 seconds. Read those two figures together. At the instant the first signal arrived saying Curiosity had begun entering the atmosphere, the landing had already been over for nearly 7 minutes. It had already succeeded or already failed. The outcome was fixed, unalterable, and unknown. Several hundred people sat in a room watching a screen show them a past they could not influence, applauding each stage as it was announced, knowing the applause was for something already historical. That's why no rover has ever been driven. It's a physical impossibility. Remote control, the ordinary kind where you act and see the result, stops working past the moon and never starts working again. Nobody has ever had a conversation across the solar system, and nobody ever will. By the time your instruction reaches Jupiter, The spacecraft you were addressing is half an hour into a different situation, and its reply describes a moment that's over an hour gone. There's no shared now, there's only correspondence, a permanent exchange of letters between people who can never be in the same room. Which brings me to the thing I can't put down. Uranus and Neptune have been visited exactly once in the entire history of our species, for a few hours each in January 1986 and August 1989, by one spacecraft older than most people alive. Everything we know about the two outermost planets from close range came from those hours, gathered by 1970s electronics. There's nothing on its way to replace it. There hasn't been for over 35 years. Not because anyone thinks it's unimportant. Planetary scientists have ranked a Uranus mission among their highest priorities precisely because the data is so old. A Uranus orbiter launched in the early 2030s would arrive in the 2040s. The transit time is longer than the planning horizon of the institutions that would have to fund it, and longer than most of the careers that would have to build it. That's what the real distance costs. Not fuel, not money. It costs the outer half of our own solar system, held just far enough away that reaching it takes more continuity than a human society has yet managed to sustain. So the next time you see one of those diagrams, you'll know the numbers underneath describe orbits rather than gaps, that the spacing has been squeezed by a factor of thousands to fit the page, that the little gray one at the left-hand end is our closest neighbor and the hardest of the inner worlds to reach. Everything you were shown as a child was true, and it was drawn in the wrong unit, on the wrong kind of paper, in a shape that doesn't exist. Ask how far away the planets are, and the honest reply isn't a number at all. It's a question back. When would I be home?